All right, hello everybody. This will be my video on alkene reactions, and so this will serve as a good reminder for OChem 2 students coming up on their first midterm, and also a good study guide for OChem 1 students who are studying for the final. And so first we're going to start with a few basic reactions and give you some examples and run you through them and basically distill the important information you need to know when tackling these problems with alkenes. And so just to go into a couple reactions, first of all, there's the halogenation reaction. So this is the first reaction we're going to cover, and basically throughout all these reactions you're going to be using alkenes, and they're all going to go through a very similar mechanism. And so I will show all the mechanisms as I draw it here. So let's just start with something like this alkene, okay? So halogenation reaction is when you treat an alkene with some kind of acid, HCl, HBr, HI, and so maybe we'll just use HCl for example. And so kind of what you want to take away here is that normally when you have some kind of acid and you're doing a reaction with an alkene, the alkene will probably be taking a proton from somewhere. And so you can draw the arrow from your alkene, taking this proton and releasing that halogen ion. In this case, it's a chlorine, okay? So what's important to note is that the hydrogen goes on the least substituted carbon. The hydrogen goes on the least substituted carbon because you end up generating a carbocation on the most substituted carbon. And so as you'll learn, I'll draw the hydrogen here from the hydrogen you got from the HCl, and you generate a carbocation. And so the hydrogen goes on the least substituted carbon because carbocations are most stable on the most substituted carbon, and due to hyperconjugation effects that you'll learn later. And so this is kind of the key thing you want to take away from these alkene reactions, is that most of the time when the alkene attacks something or takes something, like taking a hydrogen or taking some other atom, and you generate a carbocation, that carbocation will generally go to the most stable carbocation it could possibly be. And in this case, it's a tertiary carbocation, or the most substituted carbocation, okay? So that's something that's important to take into account. So once you have this tertiary carbocation here, you have the Cl ion, and that has a lone pair, which can attack in, and that would give you your product, which is right? And so in this case, we don't have stereochemistry, but in cases where we do have stereochemistry, remember that this is going to be, you'll end up with a racemic mixture because carbocations are flat, and so you can get attacked from either face, right? So, say you have something, so something you have something like this, for example. If you treat it with HCl, you would get a racemic mixture of you get a 50-50 mixture of both, because the chlorine could come from one face or the other face. There's nothing really swaying it to go one over the other. So you get a racemic mixture in that case. And so I think halogenation reactions are typically the most simple reactions for alkene reactions, but they kind of showcase kind of the general sense of how these reactions work, right? Alkene normally acts as kind of a nucleophile, takes a hydrogen or attacks some atom, and then you get a carbocation in the most substituted position, and then another atom can attack in or add in to get you your product, right? And let's just continue. So hydration is another reaction. Very similar to halogenation, just with water. So this is typically done. So we're going to use the same molecule again. It's typically done with acid and water. So, typically something like H2SO4, sulfuric acid, and water. So the mechanism for this, so maybe I'll just draw the product first. Again, it's the same thing, but you're just going to get a water instead of a chlorine. OH, right? So the mechanism for this is that in situ, you're going to get some kind of hydronium ion, so H3O plus, right? Then your alkene is going to grab the hydrogen like this, okay? And again, the hydrogen goes on the least substituted carbon because the carbocation is most stable on the most substituted carbon, okay? Again, I'll draw the H here just to, reiterate. Then a OH comes in, or water attacks. This will give you this intermediate. And I'll just draw all the steps just to be safe. And then another water can come in to pronate like this to give you your end product. Okay, so that's another important reaction. So halogenation will get you a alkyl halide on the most substituted carbon. Hydration will get you an alcohol on the most substituted carbon. Okay, moving on to a very important reaction. I consider typically probably one of the most important reactions that you'll learn in OChem 1. And probably the only reaction in OChem 1 that will teach you how to add a alcohol anti-Markovnikov or to the least substituted side, right? So, as we saw in hydration, you add alcohol to the most substituted carbon, but in hydroboration, you actually add it to the least substituted carbon. So I'll kind of just draw it here. So hydroboration, and I'll give this a star, 2 stars, because I think this reaction is something that could help you a lot and something that you definitely should know, okay? So remember how in hydration, we added an alcohol to the most substituted carbon. Here we're going to add it to the least substituted carbon. And you do this by using reactants borane or some kind of, borane complex. Hydrogen peroxide and sodium hydroxide. Okay? And so again, this will get you, and I'll talk about stereochemistry later. Oops. This will get you, in this case, you get kind of a racemic mixture here, but doesn't matter. Anyways, so it'll get you a alcohol on the least substituted carbon. That's the most important part. And so the way this happens is that when you add borane, B, right, you kind of get this coordination, this square coordination here, okay? And so the reason why the boron goes in the least substituted carbon is because boron's actually less electronegative than hydrogen is. And so, when you have something like HCl, hydrogen's the least electronegative atom there, compared to HCl. Like, you know, when you did it with the hydronium, like the OH is less electronegative than the O, but here B is actually less electronegative than H, and so that's why B goes on the lace substituted carbon. Okay, and so you can kind of, you know, draw the arrows like this, and you get this kind of complex, right? I'll just draw it like this to make it more clear. Yeah, you get that, okay? Realize that the H and the B add from the same face, right? That'll become important later when I talk about stereochemistry here. Okay. Oops. So now you have this. Now, sodium peroxide or hydrogen peroxide that is deprotonated. Oops. Sodium peroxide that's deprotonated by the NaOH comes in, attacks the B. This gives you H, and this is H2. So now boron has 4 things connected to it, so it has a formal negative charge, right? Boron doesn't really want this formal negative charge, so what's going to happen is a migration. So this bond from C to B goes to C to O, and it kicks the OH out, okay? So you're going to get H2, okay? And then the OH that got kicked out is going to be OH minus, right? And so that can come in and attack the B, kick it off the O, and so you're going to end up with a anion, an oxyanion, like this, which then can be protonated, right, to get you your product, okay? And so the reason why stress hydroboration is, you know, very important for you to know is because right now, at least for when you're learning alkenes and stuff, it's kind of one of the only ways you know how to add anti-Markovnikov, or to the least hindered carbon, least substituted carbon. And so that's, you know, useful in many cases if you're doing a synthesis problem where you know, need a functional handle on the least substituted carbon, and you have an alkene. You could always use hydroboration, and then you turn that alcohol to many different things, right? So maybe I'll put this in with the hydroboration part. So, you know, important, you know, cool reactions, you know, with alcohols. So an alcohol can be a nucleophile if you deprotonate it, right? And you can make, you know, ethers and esters, you know, different things. Oxygen could be a good nucleophile, but alcohols can also be turned into good electrophiles as well if you know, you can turn them into chlor. So maybe I'll write this down. So maybe I'll just write this down here. Alcohol to good leaving groups. Right, so there's 2 ways to do it. You can either turn them into a halogen. So say you know, just any, let's just use this for example. So say you have this alcohol here, okay? You want to turn this into a good leaving group. And so, you know, you can use PBr3. Right, that will turn the alcohol into a bromine. You know, alkyl halides are good leaving groups, but it'll invert the stereochemistry, right? So this will turn to a bromine, but instead of wedge or dash, it'll be wedge, right? So you invert the stereochemistry, and so when you add a nucleophile, you turn it back. So you end up overall retaining stereochemistry, right? So you add a nucleophile to this, you'll end up retaining this original stereochemistry, right? So if you compare the original to the end, right, their stereochemistry is retained. Oops. Retained. Okay? Another way you can turn alcohol to a good leaving group while, you know, swapping stereochemistry is through sulfonyl esters, right? And so, you know, if you have the same thing, You can mesylate, tosylate, triflate it. So, let's just do mesyl chloride. So MSCl, usually use DMAP or pyridine, or, triethylamine, whatever. Whatever, nitrogenous base, and you get something called a mesylate, right? So now you see, because the alcohol attacks the MSCl and not the MSCl attacking the alcohol, the stereochemistry at that position doesn't switch, right? It's retained here. Also, maybe I'll include what MSCl looks like. Okay, so it's retained, and so when you add a nucleophile, overall, there's inversion. Right, so these are just two ways you can turn alcohols to good leaving groups. And so when you're doing a synthetic problem, right, where you have maybe an alkene on your starting material, and you need some kind of functional handle, and the least substituted position, maybe it's a primary position, right? You can turn it into alcohol, and then you can turn it into halide, and you can make a Grignard from that, or you can, use it as an electrophile. There's so many things you can do, and that's why I find that hydroboration so useful for you to know, is because, there's really so much you can do with it, right? And it's really, right now, probably the only way you guys know how to do anti-Markovnikov addition to alkenes, right? It's hydroboration. And alcohols are so versatile, right? Okay. Oh, and then let me get to stereochemistry of hydroboration as well. Okay. So okay, so this is also important. So remember the start of hydroboration when I said the boron and the hydrogen attack from the same face? That dictates the stereochemistry. So let me just give an example here. So imagine we have this cyclohexene, okay? It's methyl cyclohexene, okay? If we do hydroboration on it, right? The stereochemistry is specific, relatively, right? And so you'll get, this is important, you'll get the methyl group and the alcohol group anti to each other, or the hydrogen and the alcohol syn to each other, right? Because again, if you think about it, right, the boron, like I said, in the beginning when I was explaining hydroboration, the boron and the hydrogen add from the same face, right? So they add from the same face, and so whatever substituent, say, in this case, the methyl group that is with on the same carbon as the hydrogen is going to be anti to your alcohol, right? And so I think that's important to point out too. There is stereochemistry here. So there's relative stereochemistry here. Okay. Moving on. There are also just a couple, maybe I'll go quicker through these ones because we kind of already went over the basic concepts of alkene reactions. They all kind of follow the same thing. But in this case, we're going to go into, let's do halogenation. So halogenation is when you you add Cl2 or Br2 or I2 to an alkene. And so, again, if you have this, right, if you add Cl2, you would get there's no chiral center here, but I'm just going to draw it that way. Okay, so basically how this works is, right, Cl, Cl, and you get this intermediate. Okay, whatever it is, it's going to be, this is, afterwards, the other Cl is going to attack the most substituted position to release this, and that'll get you your, your double chlorinated product, and the chlorines will be anti to each other, right? And so, the stereochem of this is going to be halogens are anti. I think that's, basically what you need to know. So, if you had like something like this, I don't know, right? No, you know what? Let's just make this even easier. So if you had something like this, right, and you treat this with Cl2, you're going to end up with, right, the Cls are going to be anti to each other, okay? Right? And then hydrohalogenation is very, very similar. But instead of a chlorine attacking, it's just water, right? So that's what happens when you do this, Cl2 and H2O. You end up with, and the alcohol is going to be on the most, substituted carbon, make a halohydrin, right? And so the mechanism of this is the exact same, except that instead of the Cl minus attacking, right, here, it's an OH instead, or H2O, right? Basically a water comes in and attacks, and you make your alcohol, and then, you get your product. It's the same kind of mechanism, same thing. So it's literally the same. So I won't really go over the mechanism for this, but it's the same thing as the halogenation. It's just that the OH, it comes and attacks. Okay. Other things. How about, let's do epoxidation. So epoxidation is kind of important. So epoxidation, it's kind of simple. What you need to know is that you use a reagent called MCPBA. Okay, so if you have let's change up the. So let's do this. Whatever. Let's just do this. Okay. Use something called MCPBA. You get an epoxide like that. Okay, epoxide is 3-member ring, oxygen in the middle. Okay, so MCPBA is meta-chloroperoxybenzoic acid, so it looks like this. Let's just do this. Metachloro. Looks like that. Okay, and this is basically your epoxidation reagent. And so, there's a couple of things you need to know. You need to know that you need to use MCPBA on alkenes to make epoxides. You need to know that the epoxides are, going to be cis. And you got to know how to open them. Okay. So this is important. So there's two different openings. There's acidic opening and there's basic opening, okay? So under basic conditions, if you're an epoxide, and you want to open it, say you use, NaOH, sure. NaOH and water, right? The nucleophile is going to attack the least sterically hindered side. Okay, so you're going to end up with, it's not chiral, but you're going to do an SN2 attack on this thing. And you're going to attack the least hindered side, because that's the side that's most available. Nothing's favoring attacking the most hindered side. It's more favorable to attack the least hindered side in the basic case, okay? So you end up with these diols, right? This is another way you can make diols, trans diols. You make trans diols this way, okay? Under acidic conditions, right? You know what? Yeah, that's fine. Under acidic conditions, you actually open at the most hindered side. And this is kind of the same, I'll draw it out. So, say you have this, right? Let's say you're using acidic conditions to open. So, H2SO4 and H2O, okay? It's not the best example, but I just want to show, it doesn't really matter, but I just want to show that it opens on the other side, okay? So this gets protonated because there's acid here, right? So you get this intermediate. I'm gonna box this. So this looks extremely similar to this chlorinium ion. Right, so we have this, looks, very similar. They're not equal, obviously, but they look, they're quite similar to each other, in a way. And so you remember when we did a halogenation or hydrohalogenation, the chlorine attacks that intermediate at the most hindered position. The same thing goes when you're opening epoxides under basic conditions. It's the same thing, right? So that's, I guess, a way you can remember it is if you know that this intermediate, you make this three-membered ring, this, formally positively charged three-membered ring, you'll attack the most substituted position, kind of like how you did in halogenation, right? So if you had a nucleophile, in this case it's water, right? You get attack here, right? Instead of the least substituted position. So the thing to take away here is nucleophile opens at least substituted position. Right? And then here, nucleophile attacks most substituted position. Okay, that's what you need to take away from this. So what you need to take away from epoxide opening is that MCPA turns alkenes to epoxides, and under basic conditions, the nucleophile attacks at the least substituted position, but under acidic conditions, it attacks the most substituted position. Okay. Perfect. Okay. Oh, reductions. Right. So I'll just go through all of them. So if you want to convert a alkene to a alkane, use what we do called hydrogenation. So use palladium on carbon and hydrogen gas. That's all you need to know. Palladium on carbon, hydrogen gas get you from alkene to alkane. If you want to go alkyne to alkane, same thing. Palladium on carbon, hydrogen gas. It could be platinum on carbon, but palladium carbon is generally what's used. Same thing. Alkene or alkyne to alkane, palladium on carbon, hydrogenation. PD/C, H2. Simple. If you want to go alkyne to cis alkene, use Lindlar's catalyst. Right? So just put Lindlar's cat, hydrogen gas, and you'll get a cis alkene. Okay. If you want to go to a trans alkene, you can use a sodium metal reduction. So sodium metal, liquid ammonia, some solvent, and you'll get a trans alkene. Okay, but I think the top three are the alkenes you need to know. Okay. Am I forgetting something? Oh, ozonolysis, right? Ozonolysis. Okay, skip this part until I get to the ozonolysis. Okay, so ozonolysis. So ozonolysis is a way you can cleave alkenes to make carbonyls. So let's say you have this alkene. You treat it with ozone and a reagent like dimethyl sulfur, Me2S, you'll cleave this double bond to make two carbonyls. So you can think of it as, if we number this, you're cleaving the double bond between 2 and 3, and you're making 2 new molecules. So let's just make 5 here. So if we cleave this, you're going to end up with these two. Okay? So you get a aldehyde out of this, so ketone. So this 1, 2, and 5, and you get an aldehyde. So this is 3, and 4. And so ozonolysis is really useful because it allows you to turn your alkene into carbonyls. It also allows you to cleave bonds, right? And so if you have extra carbons in your starting material compared to your product, and you have an alkene, you can get rid of some carbons by using ozonolysis, right? You can also do ozonolysis with an oxidative workup, where you add something like peroxide, and this will result in a carboxylic acid instead of a aldehyde. That's it, right? So this is 1, 2, 3, 4, 5. 1, 2, 5. You can do that. So I think that about wraps it up. I think there's definitely more alkene reactions, stuff like osmium tetroxide and sodium pyridate, or well, sodium pyridate. Get rid of the started. Right. Restart this. There are obviously a lot more alkene reactions, stuff like osmium tetroxide and making diols and other kind of reactions, oxymercuration. But I think I covered mostly the important reactions. Definitely the reactions you need to know at SFU. I covered probably all of them. But if you're interested, there are plenty of other resources, and if you guys are interested, you can always contact me asking about different alkene reactions. But I think in this video I covered the ones you definitely need to know. All right, I think that's it. Thank you.